Hi there, it's so good to see you. Welcome to Energy Flow in Global Systems, also known as the Climate Unit. So, we're going to really be looking at our textbooks, chapters 10, 11, and 12, or at least that's what we're going to be covering. But this is just going to be so much more interesting and so much more fun. So, let's just get started then. This is a big old list of everything we're going to look at in this unit, and highlighted in yellow is chapter 10, and where we're going to start is with 10.1 Global Systems and Solar Energy. So hang on to your hats, here we go. Let's just start. Let's just start with some basic definitions. So if you could open your booklet to page 3, and we're going to talk about defining systems. So a system is an object or group of objects that scientists wish to study. This is a pretty big open-ended definition right there. When we talk about an open system, we're talking about a system that allows energy and matter, two things we've talked about in science before, to cross the system's boundary. So, example would be a tree. So, energy goes in and out of the tree, as we know, and matter goes in and out of the tree. So, it's an open system. Now, a closed system is a system that allows only energy but not matter to cross that boundary. So, the Earth is an example. So, matter doesn't really leave the Earth, but energy does flow in and out of the Earth, like through the sun and so on. So, and then finally, when we talk about an isolated system, that's a system that allows neither energy nor matter to flow across that boundary. So we're going to zoom into the biosphere. So the biosphere is the thin layer of air, land, and water on or near Earth's surface, and it's made up of the following: the atmosphere, which is a mixture of nitrogen, oxygen, and other gases that extend a full 800 kilometers above Earth's surface. So this is like everything that we know and love is in the biosphere, right? So the atmosphere is broken up into the troposphere. It goes up to about 12 kilometers in the air above the Earth, sorry, and then the stratosphere, which is 13 to 50 kilometers up. So the lithosphere, that's land. The Earth's crust, it forms land above sea level and at the ocean bottoms, as well as the uppermost parts of the Earth's mantle. So that's about 100 to 2 kilometers thick, a pretty big chunk. We also have the hydrosphere that we talk about a lot. That's water. So that's water on or near the Earth's surface. So we're talking about oceans, rivers, lakes, streams, yeah, and even underground reservoirs and so on. So the cryosphere, ice. That's the water that's temporarily frozen in the polar ice caps, and yeah. So let's move on. But this is the biosphere, and this is something that if it's not important to you now, it should be. It is. It's like it's everything we have. So here we go. So the biosphere. This is kind of a graphical representation, and it's so important that I'm going to take up the full screen with it, and I'm going to spend a few minutes here. So we have our big yellow sphere, and that's the biosphere. That's what it's supposed to represent. And all this is giving is a visual representation of all the stuff that's in it. So we have the atmosphere, the ecosphere, the hydrosphere, and the lithosphere. So just because I really want to know that everyone is paying attention right now, I'm going to get you to spend a couple minutes, no, sorry, a couple seconds, just stare at that ecosphere circle. Now, hidden in there is a little bird. And well, it's actually a huge bird in real life. But if you look closely enough, and I'll give you a hint, in the picture it actually looks kind of bluish orange. So I'm going to get you to stare at that picture, just get really close and see if you can find where that bird is in this green circle in the middle. And that's actually going to be your exit question today. So just stare at it for a few seconds. You're going to have to tell me where in that circle that is to prove to me that you spent some deep time with this. Looking. And that's a goat. Now, still on page 3, we're going to talk a bit about the Earth's radiation budget. Now, radiation is the mechanism of energy transfer in which atoms or molecules emit electromagnetic waves. That's a mouthful, but we're going to learn all about it, no problem. So, when we talk about the radiation budget, we're actually talking about this idea that the Earth maintains an energy balance and a temperature balance by radiating as much energy into space as it absorbs from the sun. So, when there's a balance, the energy from the sun would equal the energy radiated from the Earth. So, if you take a little look at this picture, what we're seeing here is that radiation budget. So we see that the sun, there's all kinds of energy coming from solar radiation. So all kinds of stuff coming in there, all these electromagnetic waves. And some of them are coming inside and bouncing right into the earth, right? So they're all coming in, and some of it is reflected away by clouds and stuff, and some of it's reflected away by the earth itself by the earth itself. And then we also actually have other energy getting out in different ways, right? So this is the idea. There's solar radiation coming in and there's solar radiation going out. So when we talk about that incoming and outgoing radiation, if you could make sure you're on page 4 in your booklet right now, of the solar energy that enters the atmosphere, a full 49% of it is actually absorbed by the land and oceans. 42% is absorbed, reflected, and scattered by the atmosphere. And that 9% is reflected by Earth's surface and clouds. So now we have a fancy word. It's called albedo, and that's the reflectivity of a surface. So that's something's ability to reflect. So we're an example would be snow has more albedo than a black car. As we know, you can even like get a sunburn when you're out on the snow all day if you're not taking care, because the snow will reflect that sun right back up into your face and it'll get you pretty good. Whereas a black car, and that snow is not getting hot, right? But a black car, for example, it would get hot. You'd touch a black chunk of metal in it, it's pretty darn hot in the summer. Okay, so again, a little close up of this, we see that the sun is has all this energy coming off of it, and we're seeing that some places absorb that energy and some places reflect that energy back away. So let's talk a little bit about how heat actually stays in. So you're surely asking, why doesn't heat just radiate into space at night, cooling off Earth once the sun sets? So we also have this thing called greenhouse gases, and I'm sure we've all heard that term. But essentially what we're saying is there's a few types of greenhouse gases that are in the atmosphere. We have water vapor, which is actually a really big important one. Carbon dioxide, which we talk a lot about. Also methane, nitrous oxide, ozone, and so on. So there's quite a bit of gases in the atmosphere that make this greenhouse effect happen. And these gases essentially absorb infrared radiation released from the Earth's surface, so energy trying to get out, and transmit them in all directions. But that essentially traps the heat associated with it. So this trapping of heat in the form of infrared radiation is known as the greenhouse effect. So a few little diagrams for us. We've seen we have this albedo effect. We have some things reflect energy back out away from the Earth, but then our atmosphere is actually capturing some of that energy and keeping it in. So not all of that energy that's bounced away is actually making it back out into outer space. Some of it's being bounced right back at the Earth. Again, we're going pretty big picture right now. We're covering a lot of stuff, and we're just kind of like getting these ideas into our head because we're going to talk about a lot of them more in depth in a little bit. So, some other words that I just want in our head are climate and weather. So, two pretty different things. So, climate, we're talking about a trend in temperature, atmospheric pressure, humidity, and precipitation over a period of many years. So, when we talk about climate, we're talking about something that happens over a long period of time, like over many years. So it's a pattern, right? It's a trend. When we talk about weather, we're talking about the same conditions, those conditions, but at one place and one time. So weather changes, on the day to day, right? And climate is a long term trend. So, Shirley, you're asking, why are there so many different climates and what causes the seasons? Well, I have an answer for you. Oh, here's that goat again. Okay, so we're going to talk about angle of inclination. We're talking about the Earth's tilted axis. So the Earth is spinning around the sun and it's tilted when it does that. So that has a pretty big effect on the world. So we're going to say that the Earth is tilted at 23.5 degrees, and that has some big time effects. So since the Earth is tilted, it causes the seasons. In our summer, the northern hemisphere is tilted towards the sun. Then, 6 months later in our winter, the northern hemisphere is tilted away from the sun. Let's take a little look at some pictures to talk about it. So, again, kind of that northern hemisphere on the left, we can see it's tilted towards the sun. So it's closer to the sun, right? And it's having this like longer period where we can see the sun in the summertime, right? And then in the winter, on the right hand of that bottom diagram there, is the exact opposite. So that has a pretty big effect on us, doesn't it, right? When we look outside at different times of the year, things are a little different from day to day, right? Or from season to season, certainly. Okay, so right now, if you're wondering, we're on page 5, and I just want to point out that the warming of the Earth is unequal. So the warming of the Earth is directly affected by the angle at which the sun's rays hit the Earth, and it hits the Earth at different angles at different places around the Earth, right? Because we have that tilt going on. So the sun's rays will cause the Earth to heat up at a faster rate when they're in contact at 90-degree angle. So when those waves are hitting directly head on into the Earth at 90 degrees, just like straight into the Earth, more will penetrate, right? But if it's at an angle, more will bounce off. Okay, so the shallower the angle becomes, the less intense the sun's rays will be, and therefore the temperature of the Earth will become less intense or less high. Okay. Well, my friends, we did it. We did it! Okay, can you please complete practice assignment on page 5 to 8? And please actually get it done and make sure you fill everything out, okay? Thank you very much. Bye-bye.